Scaling an FFT and PSD, or power spectral density, in Matlab. So if you've looked online at any of the examples for FFT and PSDs, you'll notice that there's a lot of scaling factors in there. And what I'd like to do is explain where some of them come from and also try to give you a way of easily scaling to match what you might expect from measuring a signal in the lab. So if you've noticed, there is quite a bit of normalization that happens to the FFT. And the one that we use often is 2 times S, where in this case S is simply the FFT of some other signal. X is an example here. And what we have here is 2, and the 2 is because we're going from double-sided to single-sided. The FFT is S, N is our number of samples in our FFT, and Fs is our sampling frequency. And I just want to note that Matlab uses this notation where a slash and the next one is divided by. If you do another slash, it divides by the next one. So this is all equivalent to what we see here on the right with both N and Fs in the denominator. All right, so what I want to do is I want to use Parseval's theorem, which simply states that if you sum up all of the coefficients in one domain, it should equal the sum of the coefficients in the other domain, particularly the Fourier transform. So the coefficients in the time domain, the frequency domain, here in the discrete domain, and the discrete frequency domain. Notice here the 1 over n, because that's one of our scaling factors that you'll see in our discussion. So let's take a look at a physical quantity of total energy. So the total energy of a signal. And we can write the total energy as x squared times d of t. Now, it may not seem clear to us why we have to multiply by dt, so let's just take a look at what a signal might look like. And I'm going to switch to my pen here, and I will use, I think for this one, I will use a light blue. So x of n is actually just a single point. And we could sum up those single points squared, but we would miss all the additional signal. What we want to do is capture the additional signal that is there. And just to be clear, the way to think about this is I have some analog signal that's maybe like this, and I'm sampling it at these blue points. I guess if that was a correct statement, I'll just erase this. There we go. The signal would be something more like this. And to approximate it, we're just going to take one value and assume it's constant for a given time, dt. And if these dt's are small enough, we'll end up with a good approximation of our actual signal. So that's what we're doing here on the left side by multiplying by dt. And then mathematically, if we multiply the left side by dt, we're just going to multiply the right side by dt. And we can simplify this a little bit if we note that dt is simply 1 over Fs. And so we end up with the total energy over here is the sum of the coefficients scaled by n times Fs, which is equal to the sum of the coefficients times dt, which is the total energy of our system. Now, I should just make a quick note here that this total energy is for the time sampled. And why I mention this is if we have a longer time, the total energy is greater. Now, I have here a Matlab of a power spectral density and FFT. And I'll just correct this here real quick. This is meant to be a and, not a convolution. And let's just go over this code real quick. So we've got a sampling frequency of kilohertz. We can find dt by doing 1 over that. In this example, we're going to make a length vector of 15,000 points and create a time vector out of our sampling time, dt, and our signal length of 15,000 points. And what I'm going to plot is 2 signals. I'm going to plot a sinusoid at 50 hertz at 0.7 and a sinusoid at 100 hertz with 1 volt. And let's just skip down here and look at what I'm going to plot. I'm going to plot the signal itself, which is simply y equals x. I'm then going to plot the scaled PSD as we saw before. And note I have my single-sided spectrum because I'm just doing half right here. And instead of squaring it, I'm multiplying it by its conjugate, which will give me the same value of a real component squared. And I'm dividing by n FFT, and then I'm dividing by Fs. And in this problem, n and ft is equal to L. Let me just write that out specifically so there's no L equals R. Put better. N FFT equals L. And the reason you don't see it on the screen is I've cut out a little bit of the code that I have used for this. And then finally what I'm going to do is plot the FFT, which is S1. And if you go up here, you can see S1 is just strictly the FFT directly. So let's take a look. So here is the signal that I'm going to plot. Here's the time domain. You can see the two frequency components. And on the right, you see the FFT. And you can see clearly we've got the coefficient correct for the 50 hertz and the 100 hertz. It's actually plotting the amplitude of these signals. So the amplitude of each sinusoidal component is correct in our FFT. Now, and I'll just back up here, I just want to point out we're scaling by 1 over n already. So this already includes the 1 over n scaling to get us our correct points there. Now, what I've done is I've plotted the PSD exactly as I showed on the previous one, where we take the conjugate, and here we are dividing by 1 over n and 1 over Fs. Now you can see that our frequencies are correct, but if you note, the amplitude is not the power. This is maybe 3.75, and this one is maybe 7.5. What we should get for our power is we should get 1 divided by the square root of 2 squared for this one. And for this one here, we should get 0.7 over the square root of 2 squared. And so this is roughly 1/2. And we'll see the calculation of this, but I think it's around I'm actually not going to, we'll take a look at what this one is on the second one. Okay, so the amplitude is not correct for the sinusoids, but the integral of the energies is correct. If you notice here, I'm calculating the total energy, which is just v squared times dt, the summation. I get the same energy in time as I do in frequency. And so the integral of the time domain and the integral of the spectrum both give me the same energy. So I know that I've done my correct part with this scaling, but I need to figure out a way to normalize so these delta functions are the correct value. Before I show you that, I just wanted to take a quick look at the FFT, which is here, versus the PSD, and you can see clearly 0.7 and 1 are the actual amplitudes, and here we do not have the correct amplitudes, although the frequencies are the same. Let's go back and look at this idea of energy, and we're going to talk about power as being energy divided by time. And so let's take a look at the total energy we had before. And once again, I'm using Parseval's theorem, and then I'm adding my little dt in here. So this is exactly the equation we had before. I'm keeping the dt for a moment, and I'll show you why. And now what I'm going to do is I'm going to normalize by the total time of our signal. So if we sampled a signal for ½ a second, the total time would be ½ a second. And so what I've taken is the energy, which is on the top. Let me go ahead and write that. So I've got my energy here, and I'm going to divide it by my total time, and that'll give me an average power, if you will. On the right-hand side, I'm just dividing by t total because that's what I did here. Now, we're good up to here, but the question is, can we simplify further? And the answer is maybe. So what I've done here is I've gone ahead and substituted for t total n times dt. Now, this is assuming that t total is n times dt. And the assumption here needs to be careful, because if you remember, I made a time sequence t using my L equals 15,000 points. Remember that? I did that from 0 to 14,999, and I multiplied that by dt to get my time sequence. Now I could use that same number of samples for my FFT, but sometimes when people take an FFT, instead of using a number like this, they like to use a number that is an integer power of 2. So 2 to the n, where n is an integer. And you can actually take an FFT with more points than your time samples. They just pad all the points that are the difference between your time samples and the next power of 2 as zeros. So if in this case you used a different number for your FFT than you did for your time, this does not work. I just want to point that out. But in this example, we used that, and so it does work. And I can simplify further, and I can cancel out my dt's. And over here, I have some of my coefficients over n, and on the right side, I have 1 over n squared, and this is going to give me my power. Let's take a look at what this looks like. And most importantly, it's going to give me a normalized PSD. And I'll show you why that's important on our next slide. Here I've used the normalized power that I showed you before. And you can see right off the bat we have the same time domain signal, but let's look and see what we have here at in the frequency domain. So we clearly have our energy of our base signal, which is 0.5, as we'd expect. And then let's take a look here. So I mentioned before we would do this. So we've got 0.7 divided by the square root of 2. And that's equal to 0.496, or basically 0.5. And then we're going to square this, and then we get our 0.25 right there. So we indeed have the correct coefficients for both of these sinusoids here. And so with this, we end up with the amplitude for each delta function is correct. And if also you look up here at the energy, you'll notice that the energy matches. So now we have both the amplitudes correct and the integral of the energy is correct. And so we've solved our problem of scaling the FFT to give us exactly the power spectral density that we would expect, with the amplitudes being the same and the integrals being the same. What I did is I went ahead and plotted this, but I went in and I deleted this, and I did NFFT squared, where that is our number of points. Once again, NFFT equals L in this example. However, sometimes people will set NFFT equals to 2 to the n, where n is an integer multiple in doing the FFT. And this is not any special function. This is just a variable. We could have called it P or X7 or whatever variable you want. But people typically use NFFT as the number of FFT points. In our case, we didn't use this. We used it as L, and that allows us to just divide by the number of points squared. So I could have also divided by L squared in this example. So let's see what we get here. I'm sorry, this was the code for the previous one. And so, in summary here, all we have to do to scale our FFT is the first thing we want to do is we need to multiply by 2 to go to single-sided, and then we can divide just by 1 over n squared. And once again, I can't emphasize enough, this is assuming that n is used for the time series and for the FFT. If you did them separate, you'll have to find a different way to scale. But this makes things pretty easy and gives you something that you would see in the lab with the correct power for each component, as well as the correct integral when you integrate up to calculate signal to noise.